Welcome to This Explainer. Picture this. For literally decades, based on John Dalton's early atomic theory, scientists fully believed that atoms were the absolute, indivisible building blocks of matter. Everyone just assumed they were these solid, indestructible, microscopic bowling balls. But as science advanced, a massive mystery began to unfold. Spoiler alert, they weren't unbreakable at all. So what exactly makes up these supposedly indestructible atoms? Okay, let's dive right into this. If everything in the universe is just made of these solid, unbreakable little spheres, how do we explain some really weird physical behaviors? Scientists quickly realized that there had to be more to the story. There had to be smaller, hidden constituents lurking deep inside the atom itself. The very first major clue actually came from something you've probably experienced yourself. You know that thing where you comb dry hair and suddenly the comb acts like a magnet for tiny bits of paper? Or when you rub a glass rod with a silk cloth and it starts pulling on an inflated balloon? That's static electricity. And if atoms are really just perfectly neutral, unbreakable spheres, where on earth did that electrical charge come from? This everyday, normal phenomenon absolutely proved that matter, and therefore the atom itself, must actually contain charged particles. To figure this out, scientists kind of had to play detective over a few decades. It kicked off in 1886 when E. Goldstein discovered positively charged radiations that he called canal rays. Then boom, in 1900, J.J. Thomson formally identified the negatively charged electron. A few years later, in 1911, Rutherford uncovered the nucleus. And finally, Chadwick discovered the neutron in 1932. Let's look a little closer at these incredible breakthroughs. Now, what's really interesting about our ultimate suspect lineup of subatomic particles is how elegantly the whole system balances out. The electron's -1 charge and the proton's +1 charge mutually cancel each other out entirely, which makes the atom electrically neutral overall. And when it comes to weight, the proton and the neutron each weigh roughly 1 unit. But the electron, it is so unimaginably tiny that its mass is literally considered negligible. It's basically a rounding error. So, how do all these pieces actually fit together? Well, J.J. Thomson was the first guy to really take a swing at a structural model. He envisioned the atom as this sort of big sphere of positive charge with negative electrons just randomly embedded inside it. To visualize this, think of a traditional Christmas pudding, or even better, a watermelon. The red, fleshy part represents all that spread out positive charge, while the seeds studded all throughout it, those are the negatively charged electrons. Honestly, Thomson's model made a lot of sense at the time, but Ernest Rutherford wanted to really put this watermelon theory to the test, which led to his now legendary gold foil experiment. Rutherford essentially took these really fast-moving, heavy, energetic alpha particles and fired them like tiny bullets directly at a sheet of gold foil that was only about 1,000 atoms thick. Because the alpha particles packed so much mass, he fully expected them to just plow right through those watermelon atoms with barely a nudge. But the results completely shocked the scientific world. While most of the particles went straight through as expected, some actually bounced off at really wide angles. And get this, 1 out of every 12,000 particles literally rebounded completely backwards. Rutherford was stunned. He captured his own disbelief perfectly, saying it was almost as incredible as if you fired a 15-inch artillery shell at a piece of tissue paper and it bounced right back and hit you. Thomson's pudding model was shattered. To wrap our heads around why this happens, imagine a blindfolded kid throwing tiny stones at a barbed wire fence. Most of those stones are just going to fly right through the empty gaps without hitting a single thing. Rutherford realized atoms are exactly like that fence. The reason almost all of those heavy alpha particles zoomed straight on through is because most of the space inside an atom is, well, it's just completely, totally empty space. Talk about a massive paradigm shift, right? Thomson thought all the mass and positive charge was spread out soft and evenly, but Rutherford realized that those rare, crazy deflections meant all that positive charge and practically all the mass had to be crammed into an unimaginably tiny, dense center, the nucleus. To put that into perspective, Rutherford calculated that the nucleus is roughly 100,000 times smaller than the atom itself. That is wild. Now, Rutherford's nuclear model was an absolute stroke of genius, but it had one pretty glaring fatal flaw. He proposed that the electrons just revolve around the nucleus in these circular paths. The problem is, standard physics tells us that any particle moving in a circular orbit is accelerating, and accelerating charges lose or radiate energy, which means Rutherford's orbiting electrons should quickly run out of juice, spiral inward, and crash right into the nucleus. If that were true, matter, and you and me, literally shouldn't exist.
So we urgently needed a fix for this atomic collapse. Enter Niels Bohr. He basically saved the atomic model by proposing that electrons don't just orbit wherever they please. Instead, they revolve safely in very special, discrete orbits, which we call energy levels, designated as K, L, M, N, and so on. As long as an electron stays in its own special lane, it doesn't radiate any energy. Problem solved. The atom stays stable.
Okay, but what are the rules of the game here? How are these electrons actually organized inside these shells? Well, Bohr and another scientist, Barry, laid down a strict system. Step 1. The maximum capacity of a shell follows a simple formula, 2n squared. So the first shell holds 2, the second holds 8, the third 18. You get the idea. But step 2 is a big catch. Regardless of its total mathematical capacity, the very outermost shell of an atom will never, ever hold more than 8 electrons. And step 3, these shells always fill up systematically, starting from the inside and working their way out. So the absolutely crucial point is that these specific electron arrangements dictate exactly how atoms behave in the real world. This brings us to valency, which is essentially the combining capacity of an atom. You see, atoms are kind of inherently lazy. Their ultimate goal in life is just to achieve a perfectly stable, fully filled outermost shell, usually an octet of 8 electrons. To get that perfect 8, atoms will actively react with each other by sharing, gaining, or flat out losing their electrons. Let's look at some quick examples of this valency in action, because an element's whole chemical personality really comes down to those outer electrons. Take sodium. It has 1 outer electron. It's way easier to just dump that 1 than to try and scavenge 7 more, right? So it loses 1, meaning its valency is 1. Magnesium has 2, so it drops 2. But now consider fluorine. It has 7 outer electrons. It is so agonizingly close to that perfect octet, so it aggressively grabs 1 electron, which means its valency is also 1. And argon, sitting pretty with a full 8, perfectly stable, it doesn't react at all, giving it a valency of 0. It's totally chill.
All right, now that we've got the outer electrons sorted, let's zoom back deep into the nucleus to find the atom's unique fingerprint. First, there's the atomic number, represented by Z. This simply counts the total protons, and it literally defines the element itself. 1 proton, your hydrogen. 6 protons, your carbon. Simple. Then there's the mass number, or A. This is the heavy stuff. It's just the sum of the protons plus the neutrons sitting in the nucleus.
But you know, nature loves to throw us a curveball. Enter the weird world of isotopes. Isotopes are atoms of the exact same element, meaning they have identical atomic numbers and identical chemical properties, but they have a different mass number simply because they are packing a different number of neutrons. Hydrogen, for example, usually exists as protium with 0 neutrons, but it can also be deuterium with 1 neutron or tritium with 2. Same exact element, completely different weights. Which naturally leads us to a bit of a brain teaser. The official atomic mass of chlorine is 35.5. But hang on a second. How can an atom have half a neutron or half a proton? It can't. Since naturally occurring chlorine is actually a mix of 2 different isotopes, how do we arrive at a weird decimal like 35.5? The math behind chlorine brilliantly illustrates exactly how scientists solve that problem. Out in the real world, about 75% of chlorine has a mass of 35, while the remaining 25% is a heavier isotope with a mass of 37. To find the official atomic mass, we just calculate the weighted average based on this natural 3-to-1 ratio. When you average out 75% of 35 and 25% of 37, you hit exactly 35.5. So it's not half a neutron, it's just an average. And hey, isotopes aren't just some quirky textbook math problem. They have immense practical value and literal real-world superpowers. Certain isotopes of uranium are the exact fuel powering our nuclear reactors. Cobalt isotopes are critical, life-saving tools used in medical cancer treatments today, and iodine isotopes are utilized right now in hospitals to treat thyroid diseases like goiter. Now, just to make sure we're 100% clear before we wrap up, we should briefly contrast isotopes with isobars. We know isotopes are the same element with different masses. Isobars are the exact opposite. They are completely different elements with totally different atomic numbers, but by pure coincidence, they happen to share the same mass number. For example, calcium and argon. Two totally different elements, but if you add up their protons and neutrons, they both happen to hit a mass of 40. Honestly, it is just staggering to think about how far we've come. We started this explainer looking at Dalton's old idea of solid, unbreakable spheres, and we've tunneled all the way down into the bizarre, dynamic world of Bohr's electron shells and Chadwick's heavy neutrons. Which leaves us with this one final provocative thought. If we were so incredibly confident that atoms were totally indestructible just over a century ago, what hidden, mind-bending mysteries within the nucleus might we uncover next? Keep asking questions and keep exploring.